Hello, my name is Nagasai Purvaj and my roll number is 20955804009. And today my topic is the jointly Gaussian random variables of n random variables. For n random variables, first before going on to the n random variables, we have to know about two random variables of jointly Gaussian random variable of two random variables. Let's let us take the two random variables x and y are said to be the jointly Gaussian random if their joint density function is in the form of this thing is in the form of this where the x bar equal to expectation of x and y bar equal to expectation of y, and the variance square equal to expectation of x minus x bar whole square, and expectation of y equal to and variance of y equal to expectation of y minus y bar whole square, and rho where rho equal to expectation by variances of their values. And this is the form where this should be the form for jointly Gaussian random variable to be said the to be said and the random variable, and we can say that it has the maximum points located at the points of x bar and y bar. The maximum value is obtained from an equation which is this thing, which is this equation. It is obtained by using this equation, and the locus of constant values of f of xy will be ellipse, and this is equivalent to saying that the line of intersection formed by the slicing of function xy of xy is a plane parallel to x and y plane and is an ellipse. So observe, if the row is if the row is 0, then here the density functions then the density functions are the marginal density functions of x and y, which are again given by these equations now is sufficient to say that x and y are statistically independent. These equations are required are just required to say that x and y are statistically independent. So we can conclude that for any uncorrelated random Gaussian random variable, the variables are also statistically independent. So we can say that for any Gaussian density random variables, then they are statistically independent. It results that the coordinate rotation through the linear for plane of x and y through the angle of 1 by 2 tan inverse 2 rho variance of x and variance of y by whole variance by variance, or this is the expression which gives the rotation across the angle, and this rotation is sufficient to convert the correlated x and y variables having variances of x minus variances of y respectively, and the coordination coefficient of rho and the joint density is statistically independent. We have to note that the joint density of any of any Gaussian random variables are statistically independent. This is the main point for which we have to know that we have to know two random variables. For n random variables, let's go into the n random variables pool. For n random variables which are from x of 1 to x of n, they are called jointly Gaussian density function if their joint density function can be written as this function where the small x minus bar is a matrix of x1 minus x bar 1, and c of x is also a matrices of C, where C is the covariance matrix, where Cx is a covariance matrix, and Cx is a covariance matrix, and we use these notations where the bracket of 1 for the matrix transpose, and for the matrix transpose, and for the matrix inverse we use brackets of -1, and for determinants we use the determinant symbol. The n random variables are given by, for finding a random variable in n random variables, which is given by c of ij is equal to expectation of xi minus x bar I into xj minus x bar j, where it is equal to the covariance of x and the covariance the covariance value of c of x of I, where this density function is often called the invariant Gaussian density function. For special cases where n equal to 2, or for special cases where n equal to 2, the covariance matrix becomes this, because we can find the values easily in this. So the covariance matrix inverse is in the form of this matrix, where 1 by 1 minus rho whole square into this matrix, where the determinant of inverse of covariance is this. So by substituting this inverse covariance matrix of 2, we have to note that it is for only n equal to 2. So by substituting this c of x minus 1 in the values of into this equation, the result, it is easily to verify that the bivariant density of 3, it is easily verified x1 equal to y. We will get the bivariant density of, we know before that the Gaussian random variables are said to be bivariate. If then we will get this bivariant nature of this random of this density if this density function, which is because we took only n equal to 2. In this case we have took only n equal to 2. That's why we have got this expression. Again, where this expression, we know that before we know that this expression is used. This expression is used to say that the x and y are to be jointly Gaussian if their density function is in this form. So we have got this function again, we have got this expression again by substituting these values, in this function, so in this function, sorry, wrong one, in this function. So we can say that for any number of random variables, we can find their density functions by using these expressions, so now let's talk some properties of the jointly Gaussian random variables. The Gaussian random variables are defined through only their first and second movements only, and the random variables are uncorrelated. They are always statistically independent. We have to note the point that they are always statistically independent. If random variables produced by the linear transformations of x of 1 linear transformations, then it is also a Gaussian random variable. By transformating this random variable, we always get a Gaussian random variable, and any k-dimensional marginal density function obtained from the n-dimensional density function can be integrated, or it is said to be in the order of x of k plus 1 to the x of n. The conditional density function of f of x1 or density function of x1 to the x of k is always equal to the conditional density function discussed before in the chapters. So by this we have to say the overview of this lecture is that by using this value, we can say that we can calculate the density function of Gaussian random variables of jointly density function of Gaussian random variables of only two random variables. So, and by using this function, we have proven that the x and y are always statistically independent, and if there are x, y, z and x, there are always statistically independent. And by using n random variables expression for jointly Gaussian density function, we have proven that we can again reconstruct this expression by substituting n is equal to 2, and by taking this covariance inverse is equal to this value and this value. So we have to note that always the Gaussian random variable is a statistically independent random variable and can be used that any uncorrelated Gaussian random variable are also statistically independent and rotates around through an angle of this. So thank you.